this work is a joint work with my colleague Liqun, Li, and Feng Zhao in MSR Beijing, and also work with Peng, who is now at the UMass Amherst, and also Chunyi Peng from Ohio State. Actually, I feel kind of sad because the ordering is not very good. I wish that I should be the first presenter for this session because I see from the results, so our results actually is not as attractive as previous works. Yeah, but anyway, so okay, let me continue. So the reason actually for this work is still the need of higher precision. Excuse me. So okay, just now there are two papers that show that there is excellent localization accuracy, right? But I would say for talking about the indoor localization, so the Wi-Fi based method or systems are still the mainstream, especially those leveraging existing Wi-Fi infrastructure. Okay, so for Wi-Fi based method, so for a point position, I think the current state of the art accuracy is several meters. By point position means you just stand there and then take your device to make a one-shot localization. But if you allow the device to track you while you're walking, then the accuracy can be kind of improved to a few meters. So, but is this enough? Maybe if you are just trying to navigate within the mall, maybe that's pretty good. But for some scenarios, actually, we still need even higher accuracy. For example, in a library, you want to find a book, or maybe you have a shopping list, so you want to go to the grocery store. You want to get all of them in short time. And also for the merchant side, actually, they want to have precise information about where the shoppers has walked or looked at. So this is kind of enabling future we call physical analytics. And also, yeah, many people are saying, if we have a relatively precise, localization, then we can enable more natural gesture-based interaction. So all this, requires higher demand, higher accuracy. So yeah, I think, in general, human demand never ends, right? So as long as we have a good technology, definitely we can find a new interesting applications. So our solution actually is trying to leverage the visible light, in particular the LEDs. So the reason is actually, we noticed that the trend actually for the light industry, actually, we have seen the LED basically is penetrate the wide, in a fast speed. So actually, I went to some stores here like Safeway. So I noticed that for the sector of the bulbs, actually more than half of them is already LEDs. And this is because LED has a few attractive, properties. For example, it has much high. It doubles the lighting frequency if you compare with the conventional, compact fluorescent light. And the lifetime actually is significantly improved. Basically, it's 60 or 70 kilo hours. And also, it's mercury-free. It's kind of more friendly to the environment. And so currently, the cost of a LED bulb itself is kind of more expensive. But in the long term, if you calculate how much the energy it saves, it's still, long-term wise, it's still a wise decision to using LED. And also, LED actually itself is a semiconductor device, so it has additional properties which make it attractive or make it possible for us. One is actually can do turn on and off instantaneously. So, for example, for the commercial lights, LEDs, we measured. We found it they can turn on and off within 4 microseconds. And also, actually, people leverage this property to dim the LED using a technology called pulse width modulation. So basically, just tune the duty cycle of the on-off to give you a different intensity. So, and actually, this property has enabled a new field called visible light communication. Right? People kind of call it it's a dual paradigm because it's the primary purpose is for lighting, but you can still use it for communication purpose. So this work actually we're trying to maybe make it a triple paradigm. So we just want to add localization to this. So our solution is, we want to leverage the existing light infrastructure, and also we leverage the light sensors on already on the device, trying to give people a very precise positioning results. So actually, there are some, there are two particular advantages of this using visible light. First of all, it's the high density of lights. So take a look at this room, right? I just counted. I think it's over 100 light bulbs there. So how many APs can we have? I guess maybe a few. The other thing is actually, it's visible. Okay, so it's unlike AP, it's invisible. So invisible actually in some situations actually we can, especially when the human has a desire to get a high location accuracy, so it can be easily involved. Yeah, I want to emphasize here again. So our key is trying to leverage existing infrastructure. So talking about the basic concept of the Epsilon, so it's basically it's a three-step approach. So in the first step, actually, it's very simple, right? The infrastructure, okay, we are send out some information, and we using the visible link, and this information will be picked up by the device. And in the second step, we're trying to figure out what's the distance between the receiver and the multiple flights. So this is we're using a model-based approach. And then once we have the ranging from device to multiple lights, so it's kind of easy to get the actual position of the device. So in the next few slides, I'm going to focus more on the channel, on the model. So so basically, okay, this is the formula gives the channel model. So there are a few parameters there. So here, actually, the theta is the incidence angle. So basically, from the which angle the light comes into the device, and the phi is actually is called the irradiation angle. So basically, that's where the light comes out from the source. And also it's over d squared. D is the distance between the device and the light source. And also the PT and the GR here refers to the transmission power of the light source, and also the receiver gain. So the PR is the receiver signal strength. So I'm going to, we actually did lots of experiments to verify, okay, this formula really holds in practice. So the first experiment we did is trying to see how good this fits the d square. So we can see those from the figure. Okay, the cross marks actually are measured, and then the curve actually is fitted. So you can see it fits very well. So I think this is actually one of the advantages of why we can achieve better results using visible lights or using lights than using like a Wi-Fi signal. Okay. So next, I'm going to show the effect of the irradiation and the incidence angle. So here we can see actually there are. Let's first look at the two figures on the top, right? So basically, so we just change the theta and phi from minus 90 degree to the positive 90 degree. So we measure the response, and it looks still okay. Okay, then we want to if we look at this more carefully, then we want to see at a certain part of this plot. So we see there is a big gap. Okay, so we want to understand how much the real impact is going to be. So then we plot the relative the error at different angles. So that's lead to the two plots in the bottom part. So we can see as the incidence angle goes to larger, okay, actually the relative error will increase. So this says, okay, when we in real use, actually we should avoid to using this, which has a very large irradiation or incidence angles. And the other thing is actually if we look at the part, okay, near zero, actually we can see still there is a range. So basically there it's kind of flat. So that means even though for theta and phi we don't have very precise estimation, but as long as it's kind of close to the zero, then it has a very small impact on the result. Okay. Yeah, the third now we still have two other parameters to tell. So actually, there are some mathematical derivations, which is very simple, right? So basically, by on-off the modulation, so basically it's a square wave, so we can kind of expand this into a Taylor series, and then the excuse me. So the emission power actually will spread over all the spread over the baseband and all its the harmonics. So, but it's kind of impossible for us to calculate all this the leaked energy. So, but fortunately for our localizing purpose, I think it's enough to using the baseband energy. So that is we can have this the second formula basically, which is the interesting thing is actually this is kind of not related to what's actually the frequency we are modulating, but it's a function of the duty cycle. So so basically, after all this study, so we come up with a conclusion. Basically, the received energy should be a function of the duty cycle and also the irradiation incidence angles and also the distance between the source and the receiver. So now, okay, we have the model. Okay, so and as I said, the first step is to sensing, and then from the sensing part, we get the received signal strength, and then we apply a model, we are able to get the distance, and then we perform triangulation to get the real position. So in our real implementation, actually, we have some practical considerations. So one is, okay, so what kind of what kind of modulation method we are going to use, right? So in our case, actually, one of the particular constraints is, okay, we want, when we do the modulation, so we want this one won't be perceived by the human, because otherwise, people will see the flickering effect. So this means, okay, we need to modulate at a high frequency, and also when you do the modulation, okay, you should not create any rapid, not rapid, okay. Let me put it the other way. So basically, what we do is trying to using the frequency modulation, because the frequency modulation will not change the duty cycle. Okay, so you can keep a constant intensity, so that which means it will not flicker perceived by the user. And of course, we should stay away from 50 or 60 hertz interference, because this is obviously because of the existing lighting actually is already alternative. And also, when we design the frequency of the, you need to be careful about we call self-interference of harmonics, because we are using the baseband energy as the way to measure the received signal strength, right? So it's actually we should avoid any other. The baseband frequency can be a harmonic frequency of any other devices. And so another actually particular constraint from our real implementation is like we are using the commodity mobile phone. So currently, the frequency we can get from the sensor on the device is only about a few hundred hertz. So this is not enough. That's why this is purely kept by the software. Okay, because the light sensor itself is a passive sensor. Okay, you can read it actually at a much faster speed, but unfortunately we cannot get it. So what we did is actually in our prototype actually we're using we made another dedicated sensor board. Okay, so for the prototype actually I'm going to talk. There are two parts, right? One is on the light bulb. The other one is on the device side. Okay, so basically what we do is we add a small control board into the light, and then we perform the BFS binary frequency shifting keying modulation, and then this figure shows the packet format. Okay, in our communication, and on the device side actually we use an audio jack to really get the signal from the sensor board back to the phone. Actually here, so we are using the spectrum from 10 kilohertz to 19 kilohertz, actually, again, this is because of the limitation of the audio jack, right? Because the audio chip samples at most at 44.1 kilohertz. So we want to, avoid alias. So we limited the maximum frequency to be lower than that. So we divided that into 30 channels. Each channel has a 300 hertz bandwidth. So this allows us to do some frequency hopping to avoid, predetermining a frequency for each device. So basically, it's just random hops. Okay, this is the first generation of our device. You can see, everything is exposed, right? And then this is our latest development. So basically, we really make the bubbles, and also we make like a square size plug-in for this for the phone. Talking about the evaluation, okay, so basically, we conduct several experiments in typical environments like in conference room, and then in a cubic area, and in a long corridor. So actually, I'm not going to talk about the details, okay, but the conclusion is we always achieve sub-meter accuracy across various environments. And we also show a comparison against the existing the Wi-Fi based method, okay. So you can see the latest tool actually is the pinpoint and error tracker, which published in last year's. I think they represent the state of the art, okay, by the last year. So actually, we say our results is still better than them, slightly better than them. Okay. And then I think the key thing is actually, we don't really leverage existing infrastructure, and then probably, for example, for pinpoint, actually they need to dense AP, or for array track, they need to, multiple antennas for the receiver. So actually, another problem is interesting part is actually, what if there is insufficient LEDs? For example, you're working in a basement. Okay, there is only one LED. In this case, how can we do this? So the idea actually is simple, right? We want to involve the human into the loop. So for example, if you really want to get the position, so now you can see where the light source is. Then you can kind of tune your device to help us to get a better position for you. So the idea actually is simple. Suppose we have a way to figure out what's the distance from the device to the light source. Then basically all the possible positions of the device is actually on a circle in a certain plane, right? So and then in this case actually we leverage if we know, because we always know the north direction. If we know the angle between your device and the north angle, actually we are able to uniquely fix which position on that particular circle. So your device is, and this is basically the idea how to do the localization. So to do this, we have two steps, right? The first step is actually you need to orient your device towards the light source you are seeing. Okay, and then in this case, we will take the readings between the north and your current direction, and then you need to rotate your device, basically trying to from facing yourself and then all the way to facing the light source. So this actually our system will automatically identify what's the tipping point. That's where that angle actually will give you the irradiation and also the incidence angles. With these two, actually, we can give you the result. So, okay, this one is actually shows the evaluation. Okay, we can see, from this, we're using various sensors, right? For like campers, like the accelerometer to give you the. So we can see there are some noises in there, some noises there. But unfortunately, it's actually, as I said before, it's a cosine relationship. So it's the error. It doesn't affect that much. So we're still able to get very accurate result. And one thing I want to tell is look at the dashed red curve. Even we are using the simple coverage, actually we are able to get a very close result to the Wi-Fi based method. Yeah, I'm going to conclude my talk with this slide. So our lab actually are hiring, and also we are working on these directions. Yes, the third one is the direction I'm working on. Okay, thank you.
They're a little slow off the mark again. Let me ask you a question while people get ready. Actually, first I was wondering if you could just provide a little more background. So all of this depends on an infrastructure of visible light. Those infrastructures don't exist for the most part. So I'm wondering how those infrastructures are going to get deployed. I can see how you can plug just a new LED bulb into a bunch of sockets, but it needs to get the information feed and control. So are we going to have light bulbs that understand Wi-Fi and then relay via VLC, or what's the plan?
Well, actually, that's a good question. So basically, how we can, it's kind of how we can enable VLC, basically, right? So actually, this work is kind of to leverage the assumed. Okay, let me try to understand. Okay, it's my own personal opinion, right? So I think for this, to enable this, actually, maybe something we can leverage, leverage is like power line modulation, right? So basically, for all these lights, actually, we can get it, get it connected to the internet using power line modulation. And I see there are some proposals saying maybe we can using at a Wi-Fi chip, okay, to this, or at even Bluetooth chip to this. But I think that's going to be overkill, and also it's adds more cost to the device, to the light bulb. Yeah.
Okay, thanks. Very nice. Okay, so power lines and screw-in bulbs. Great. Okay, another question. Maybe, so in both this paper and the previous paper, you use infrastructures that are deployed, which allow you to localize. And we heard a good question at the back about really the privacy implications of these kinds of systems. Could you compare the kind of privacy you get in your system to the kind of privacy you get in the other system?
Okay, I would say the privacy or security actually is the strength of using visible light, right? Because it never exists, outside of the walls. Yeah, so yeah, so it's okay.
That's good. So there's a dimension other than accuracy. Yeah.
Oh, okay. Yeah. Thank you, David.
Yeah, I wanted to know what the limiting factor was in the resolution that you're able to get. I mean, if you're sampling using 19 kilohertz versus sampling versus the previous example where they sampled at sub-nanosecond, there's a massive range in fidelity. Is that the cause of the accuracy differences between the Wi-Fi and the visible range?
Okay, I think if we're using a higher frequency, I don't see much influence on the localization accuracy. But definitely helps. For example, in that case, we can get multiple channels, right? So so in this case, maybe we can get less confliction, less collision. Okay, so when you do the frequency hopping, so yeah, I would say okay. The reason is actually we are using very basic frequency modulation, frequency key BFSK. Okay, let's put it. We are using this very simple modulation method, right? So if you, I guess if you can have higher the range, I think we can definitely achieve maybe a higher communication rate. But for sake of the localization accuracy, I don't see much impact there.
Okay, just a related question. I mean, in a place like this where you have maybe line of sight with 10, 15, 20 LEDs, light bulbs, would you expect that the localization accuracy is going to go to centimeter level? I mean, what?
Definitely, it will help because in our when we do the experiment, we have 5 lights there. So actually, so we can always select the better 4 to give we can see there is a significant improvement. But actually difficult for me. Qualitatively I would say yes, it will improve. But how much they can improve, say to a centimeter accuracy, I'm not quite sure.
So how does the orientation of the phone affect these accuracy numbers?
Orientation. So actually, the orientation will affect when there is insufficient light sources. If there are multiples, actually, the orientation doesn't matter, right? So But if there is only one light source, actually this will directly affect the localizing accuracy. For example, because we are using the orientation to really to tell which point on that circle, right? So if let's say if you get a reverse orientation, that means you are going from this point or jump all the way to the other point on the same diameter, right? So that means. But in general, let's say I would say maybe if the orientation error is 60 degrees, that means you will get about the maybe 1 or 2 meters accuracy accuracy loss. Yes.
Okay, folks. Well, we're right on time. It's time for a break. We're going to resume at 3:45. Please thank Jackie and the speakers.